In this lesson, we're going to talk about a method called Anova. And Anova is a way to compare several means at once. So if you have more than two means, then rather than run a 2-sample z-test or a 2-sample t-test multiple times to compare each possible pairing of the means, we can run an Anova test and do it all at once. So statisticians came up with a method called analysis of variance. And that's where the Anova comes from. When we abbreviate that, that's the Anova. What we're going to do for an Anova test, we're going to set up our hypothesis where all the means are equivalent. That's going to be our null hypothesis, where as if nothing has changed. So depending on how many groups you have that you're comparing, you're going to have that many means. So let's say, for example, you have 4 groups. Then you would say mu1 is equal to mu2, which is equal to mu3, which is equal to mu4. Now, for your alternative hypothesis, you would just say, since you're trying to see if something has changed, then you just want to show that at least one pair of means is different. And then, of course, in your step 1, as usual, you state your level of significance. Now, when you're stating your type of test, since we're doing this on several groups and trying to compare many means, we would state that our method is Anova. And then we would use an F distribution. And we would look for our F critical value. Instead of using a T critical or a Z critical, because we're using an F distribution, we would find an F critical, and I'll show you how to do that in a moment. And then you're also going to look for your p-value. Now, with the F distribution, you're still going to find your rejection region. However, when you draw your graph, an F distribution looks like this, and it's always going to be right-tailed. Now, when you're looking for that cutoff point to define your rejection region, and you're looking for that F critical value, there's a couple things that you need to know. To find your F critical, unfortunately, there isn't a way that I know how to do that on the calculator. There is no inverse F. So what we're going to have to do is use the tables. I've tried to let you use the calculator as much as possible up to this point in the class, but at this point, we're going to be forced to use the tables. So when you find your F critical, the things that you need to know your alpha level. You need to know what's called your degree of freedom numerator. And that is basically just the number of groups you have and you subtract 1. So for example, if you have 3 samples or 4 samples, you take however many samples you have, however many groups, and you subtract 1. So if you have 5 groups or 5 samples, your DFN is going to be 4 because you just subtract 1. Then you're going to find your DFD. This is degree of freedom for the denominator. And this is going to be the total data values minus the number of groups. So if in all your samples all together, you have, say, 50 values for all of them together. Let's say you have 10 values in 5 groups. So you have total of 50 values. Then you would take 50 minus the number of groups, which would be 5, and so your DFD would be 45. Okay? Then you're going to look it up on the table, and I'm going to show you how in a minute. You look it up on the table, and then you can find your F critical. And then step 4, you use your p-value. So step 3, just like before, it's the rejection region. We just have to do it a little bit differently using the tables because we don't have that function on our calculator. And then, of course, in step 5, we write our conclusion as normal. I have 3 examples that I can walk you through slowly, step by step. So in the first example, it says, a psychologist is studying the effects of dream deprivation on a person's anxiety level during waking hours. Brain waves, heart rate, and eye movements can be used to determine if a sleeping person is about to enter into a dream period. 3 groups of subjects were randomly chosen from a large group of college students who volunteered to participate in the study. Group 1 subjects had their sleep interrupted 4 times each night, but never during or immediately before had a dream. Group 2 subjects had their sleep interrupted 4 times also, but on 2 occasions they were awakened at the onset of a dream. Group 3 subjects were awakened 4 times each time at the onset of a dream. This procedure was repeated 10 nights, and each day all students were given a test to determine their levels of anxiety. The data in the table below is recorded the total test scores for each person over the entire project. Higher totals mean higher anxiety levels, and we're going to use a 5% level of significance. Okay, so I have 3 groups here. And so since comparing more than 2 means, I want to use Anova. So as you can see, when you look at group 1, I'll label this N1 for the sample size. When you count that up, there's 6 people, okay, in that group. Then for group 2, if we count that up, we have 7. And then in group 3, the sample size is 5. We're going to outline the procedure here for Anova, and we need to first identify what our number of groups are so that later on we can find our F critical. So we have the number of groups is 3, and the total number of data values is, let's see, 7, 6, 13, so that's going to be 18. So that tells me that the degree of freedom for the numerator is going to be 2 because I take the number of groups and I subtract 1. Then my degrees of freedom for the denominator is going to be 15 because I take the total number of values and I subtract the number of groups. So I have 18 minus 3, which gives me 15. Okay, so that's going to help us later when we have to look up on the table to find our F critical. Okay, so to set up our hypotheses, because this is an Anova and we have 3 groups, our null hypothesis is going to be mu1 is equal to mu2 is equal to mu3. So we have 3 means that we're comparing because we have 3 groups. Then we have the alternative hypothesis. We want to show that at least one pair is different. Another way you can write that is that mu1 doesn't equal mu2, which doesn't equal mu3. So either one is fine by me. You can write it either way. So for step 2, we're going to write down that we're going to use the Anova process. So I need to find my test statistic for my F, and I need to find my p-value. I also need to find, for step 3, I need to find my F critical so I can draw my graph and find my rejection region. So I need to find these 3 things. First, we're going to use the calculator to find our test statistic and our p-value. Calculator, the first thing you want to do is enter all your data. So you're going to hit the stat button. Then you're going to go into the edit option. And you're going to enter your lists or your groups into your list. So put all the information in group 1 in L1, all the information in group 2 in L2, and all the information from group 3 in L3. So pause the video and make sure you have those data values in there, and then you can unpause and we'll continue with the process. Okay, now that you have your data in your list, then you're going to go to and hit the stat button again, but this time you're going to arrow over to test because we're going to go do the Anova test. Now, the Anova test is the very last option, so you can scroll all the way down. I like to just hop up one, and it will go from the first to the last a lot more quickly. So just hop up one using your up arrow button, and you'll see that the last option, option H, says Anova. So I'm going to hit the enter button on Anova. It's going to bring me back to my home screen. So this looks a little bit different than what we've done before with the hypothesis test. But what you want to do is you want to tell the calculator which lists contain the data. So since we put our information in list 1, list 2, and list 3, I'm going to tell the calculator in the parentheses, I'm going to hit second 1 to access the L1 button. Then I'm going to hit the comma button, and then I'm going to tell it the next list is list 2. So I'm going to hit second 2 for my list 2. Then I hit comma, and then I'm going to tell it list 3. And then I'm going to close my parentheses. I'm not sure if that parentheses, if you don't close it, if that's going to affect your value. So I would just make sure you do it just to be on the safe side. Then you're going to hit enter, and it's going to give you all the information you need. Now, this stuff that's down below here where it says factor, all that stuff below there, we're not going to cover that in this class. We're just going to focus on the F test statistic and our p-value, which is given here. So here's our test statistic, 8.2124 or 5 if we round up, and then our p-value is 0.0039. So I'm going to write down that we got our test statistic for F, 8.212, and then we got our p-value is 0.0039. Now I'm going to go through, let me leave myself some more room here. Now we're going to go through and draw our rejection region. So I need to find my F critical to find that cutoff point. So this is when we're going to have to use the table. Up to this point, we've used inverse T or inverse Z, but there isn't that option on our calculator. The tables, it's a PDF file that I put in the modules. You should see it in the introductory module, but I also put it in this week's module as well. And that way you won't have trouble finding it, and it's right there. So you'll have it in those 2 places. Now, you're going to come down and see that the table for the F critical values is at the end of this document. This document is fairly lengthy because it has all these tables in it. So you want to look at the end of this document. So we're going to scroll through and find at the end where it says F critical. Okay, so we have our critical values for F, X, table I. Now, what we're going to do is, since we know we have an alpha level of 0.05, we are going to look for the page that has where it says area is equal to 0.05. So here's the first page. Usually there's probably 2 or 3 pages that has each area on it for each alpha level. So this is what your table looks like. You find your alpha level. So for us, 6.05 for this one. Then you're going to look at your degrees of freedom for the numerator. That's across the top. For us, our degrees of freedom for the numerator was 2. So I'm going to be looking in this column right here. For our degrees of freedom for the denominator, that comes down here along the side. For us, we had 15. So I'm going to find where those two cross. So if I come across at 15, and then I come down at 2, my F critical is going to be 3.6823. So I'm going to write down that my F critical is 3.6823. So that's my cutoff point right here. So now I'm going to look at my test statistic. My test statistic is 8.212. So that certainly passed this 3.6823 cutoff point. So I would say, since it's in the rejection region, I would say reject the null hypothesis. Now we're going to look at the p-value. Our p-value we got was 0.0039. That is definitely less than our alpha. And when it's less than our alpha, we say reject the null. So now for our conclusion, we're going to write at the 0.05 level of significance, there is enough evidence to suggest that at least one mean is different. So now that we went through the first example step by step, and I showed you how to access the function on the calculator and how to put your stuff in the list, and then I also showed you how to use your degrees of freedom to look it up on your table, we can go through the next 2 examples a little bit more quickly without having to stop and go back and forth between the calculator and the tables. But if you need to go back and review something because you forget how to look it up on the table, make sure you go back and look in example 1. All right, so for the second example, it says a psychologist is studying pattern recognition skills under 4 laboratory settings. In each setting, a 4th grade child is given a pattern recognition test with 10 patterns to identify. In setting 1, the child is given praise for each correct answer and no comment about the wrong answers. In setting 2, the child is given criticism for each wrong answer and no comment about the correct answers. In setting 3, the child was given no praise or criticism for wrong answers or no comment about the correct answers. In setting 3, the child is given no praise or criticism, but the observer expresses interest in what the child is doing. Then in the last setting, the observer remains silent in an adjacent room watching the child through a one-way mirror. A random sample of 4th grade children was used and each child participated in the test only once. And the test scores with the number of correct for each group are in the table. We're going to use a 5% level of significance. Okay, so in step 1, we're clearly using Anova because we have 4 groups here. So we're going to set up our null and alternative hypothesis. Since we have 4 groups, I'm going to set it up as mu1 is equal to mu2 is equal to mu3, which is equal to mu4. For the alternative hypothesis, we just want to find that at least one of those are not equal, so we're going to set it up like this. And our level of significance is 0.05. In step 2, we're going to state that we're using Anova, and we're going to find our F-test statistic and our p-value. So take a minute, enter that data in on your calculator, and do the Anova test. And then when you're done, unpause it and check to make sure you got the same answer that I did. Now, because you're entering a lot of data for these, go slowly and make sure that you're typing it in correctly so that it doesn't throw your answer. If you don't get the correct answer that matches with mine, it is probably because you entered something incorrectly on the calculator. Go back and check. For your F-test statistic, you should get 6.377. And for your p-value, you should get 0.0048. Now, for our rejection region, we got to find that cutoff point so that we have 0.05 area to the right. With Anova, we always do right-tailed test. So we have to find our degrees of freedom so that we can look it up on the chart. So for our degrees of freedom, for our degrees of freedom for the numerator, that's the number of groups that we have minus 1. Since we have 4 groups, our degrees of freedom for the numerator is going to be 3. The degrees of freedom for the denominator is going to be the total number of values, and then you subtract the number of groups. I pre-counted these, and there were 20 of them, so there's 20 data values here, and we have 4 groups, so we're going to do 20 minus 4, and we're going to get that our degrees of freedom for the denominator is 16. So pause the video for a minute and use the table to look up the page that has an alpha level of 0.05 and with these degrees of freedom here and see if you can find the correct F critical. When you look it up on the table, you should get an F critical of 3.24. Now, when we check that against our test statistic, 6.377 falls in that rejection region. So we're going to say reject the null hypothesis. For step 4, we're going to use the p-value, 0.0048. That's less than our alpha level. And whenever the p-value is less than our alpha level, we say reject the null. So in step 5, we're going to write our conclusion. So we're going to say at the 0.05 level of significance, there is enough evidence to suggest that at least one mean is different. Okay, let's go on to the last example. Okay, it says, where are the deer? Random samples of square kilometer plots were taken in different ecological locations of Mesa Verde National Park. The deer counts per square kilometer were recorded and shown below in the following table. Shall we reject or accept the claim? Well, you shouldn't be using that word. Just remember, you should always use reject or do not reject or fail to reject. It's not a good idea to use accept. Should we reject or not reject the claim that there is no difference in the mean number of deer per square kilometer of these different ecological locations? We're going to use a 5% level of significance. So this is definitely going to be an ANOVA because we have more than 2 means that we're comparing. We have 3 of them here. So when we set up our hypothesis, we're going to have mu1 is equal to mu2 is equal to mu3. For the alternative hypothesis, you can say in words at least one mean is different, or you can just write it like this. Our alpha level, again, is 0.05. For step 2, we're going to use ANOVA to find our test statistic for F and our p-value. So pause the video and see if you can get those values. You should get, when you're done, that your test statistic for F is 3.236 and your p-value is 0.087. Now we're going to set up our rejection region. So we need to find the cutoff. So I have an area under the graph of 0.05. So we need our degrees of freedom for the numerator and our degrees of freedom for the denominator. So the degrees of freedom is going to be the number of groups we have minus 1. Since we have 3 groups, when we subtract 1, we're going to get that our degrees of freedom for the numerator is going to be 2. Now, we're going to find the degrees of freedom for the denominator. When you count up all the values, you'll see that you have 12 values. And so we're going to take 12 minus the number of groups, which is 3, and that's going to give us 9. So pause the video, go to the tables, and find the page that has 0.05 with the degree of freedom with the numerator is 2 and for the denominator 9. See if you can find the correct F critical. You should get that the F critical is 4.26. Now, when you look at the test statistic, you're going to see that that falls on the outside of that rejection region. So we're going to say, do not reject the null hypothesis. Step 4, we're going to use the p-value. We got that the p-value is 0.087. Now that is greater than 0.05. So whenever the p-value is greater than our alpha value, we say do not reject the null hypothesis. So for our conclusion, we're going to write at the 0.05 level of significance, there is not enough evidence to suggest that at least one mean is different.